Hello, in this video we will be covering the concepts of velocity and acceleration when a body is moving in a circle. In the case shown in this problem, a body starts at point P and moves in the circle shown in the diagram, centered at O, at a fixed angular velocity, omega. We want to find the linear velocity of a direction and magnitude of the body as this moves about the circle. However, remember that the direction is always going to be changing because the linear velocity will always be going from P to P1, then it could be going here, here, here. So the direction is continuously changing, right? So we just want to see if there's some sort of pattern in the direction as the radial vector is changing. We first define the original radial vector, or OP, as shown in the diagram. Let this be defined as R equals to R cosine theta I plus R sine theta j, as shown here. Okay? Let the radial vector OP prime define the vector made after a small movement is made around the circumference of the defined circle. This means that by vector addition, we can tell that OP prime equals to OP plus PP prime. As PP prime is just a small change in displacement of the particle P after all, we can just denote it as S, where S is, again, a small vector. This means that our velocity must be expressed as ds over dt, as velocity is defined as change of displacement over time. And remember, S is nothing but a displacement because moving from P to P prime implies that it's just a displacement, right? That means that we are just trying to differentiate ds with respect to t. Remember, finding the displacement over time just means that we're just trying to differentiate the original radial vector with respect to time, because this theta was, after all, continuously changing, as shown here. It will become, this d theta is very small, it tends to 0, but as time passes, it's going to become bigger and bigger. So what we're going to be doing is that we're going to be differentiating our original radial vector with respect to time. This gives us r times cosine theta plus d dt I plus sine theta times d dt j. I and j, remember, are component vectors. Okay, now to do the differentiation, we're going to break d over dt into d over d theta times d theta over dt. Doing this computation, we end up resulting with the final vector r times negative sine theta times omega I plus cosine theta times omega times j. Or omega can come out of this bracket, giving us omega r times negative sine theta I plus cosine theta j. So this gives us our velocity vector. But remember, we just want to find a pattern in our velocity vector, so let's see if we can relate it with any of our constants, such as our radial vector. What happens when we try to take the dot product of the velocity vector and the radial vector? Well, when we do that, we end up getting that v dot r equals to absolute value of v times absolute value of r times cosine alpha, where alpha is nothing but the angle between v and r. V dot r in this case is omega r squared, because remember, r also has a magnitude of r, because I know that's a bit of a confusing name, but stay with me here, okay? Times cosine theta I plus sine theta j. I forgot to write this theta here, sorry. Dot negative sine theta I plus cosine theta j. However, when we take the dot product of these values, we end up getting cosine theta times negative sine theta plus sine theta times cosine theta, which is 0, right? This just gives us that absolute value of v times absolute value of r times cosine alpha equals 0, because after all, these two values, as we see here, this absolute value of v dot absolute value of r cosine alpha equals to the 0 value. This implies that this angle alpha is 0. So therefore, this tangential vector v must always actually be perpendicular to the radial vectors. So it's indeed a tangential vector, and we can also tell that absolute value of the v vector is the same as absolute value of omega times r. Now, what about the acceleration vector, right? Because after all, since this, as we just saw, as the radial vector is going to be continuously changing, right? For one time it will be OP, then it will become OP prime. So therefore this velocity vector will go like this, then it'll go like this, and so on and so forth. So as its direction is continuously changing, even though the magnitude is the same, that means that there is going to be some acceleration. So let's try and compute this acceleration. So the way that I did this is that, remember, v equals to omega r times negative sine theta I plus cosine theta j. However, acceleration is nothing but velocity with respect to change of velocity over time, or dv over dt. If we differentiate this, we end up getting omega r times negative sine theta times d dt I plus ddt of cosine theta j. I know I wrote this a bit wrong, so I'm just going to erase it and then I'm going to rewrite it so it makes a little bit more sense, because this isn't really the right way to denote things. So don't make this mistake in like an actual test or something. Like if it's being graded based on work, it does not look good. Don't do this. Okay, much better. Let's see if I did the I did this earlier too. I should have corrected it then only. I'm so sorry. Yeah, make sure you're like when you're writing notation that you're doing it correctly. It doesn't look good otherwise, and it's considered very unprofessional. Now let's do the other one, the sine theta. Theta times d theta over dt times sine theta. Now we can just do this because this is nothing but change of theta times change of theta with respect to time. Oh, so let's just go back down here. Now we have our much better formatted differentiations. Anyway, now what we're going to do is that when we differentiate sine theta I, we end up just getting it's going to be equal to omega. In the same way, we can just compute the differentiations, and a vector will simplify to omega squared r times negative cosine theta I negative sine theta j. Do you notice something about this vector? I do. R equals to, we noticed here that r equals to this constant r, times cosine theta I plus sine theta j. Here, we have that some other constant, which is omega squared r, times negative cosine theta I, negative sine theta j. This means that a must be equal to some constant times negative of r. That means that a is just moving in the opposite direction as r. But we remember that r is trying to travel away from the center. That means that a is going towards the center. So this proves that when a body is moving in a circle, it will have an acceleration towards the center, which sounds a little bit weird, but it's proved true using the calculations. Then, also as we saw here, since the magnitude of this negative cosine theta I plus negative sine theta j has a magnitude of 1, this implies that the magnitude of a must be equal to omega squared r, which proves that a must be pointing towards the center with a magnitude of omega squared r. And that is our video about our velocity vector and acceleration vector. This concept is used in a variety of f equals to ma problems. See you.